Hello. Is somebody, you guys there? Oh, here we go. People coming on. 8DEF Project Physics. You guys are here? If yes, can somebody put in the WhatsApp group that the live stream is happening right now? Just, oh, here we go. Here are people coming on. Do. Hi, Nessa. Do. Do. Hi, Isaiah. Lauren. Hello. Okay. Where's everybody else? Only 3 people here. Maybe people forgot. Is it possible? Hi, Mr. Feldmarsh. There we go. Hi. Good. Thank you, Vanessa. Hi, Liam. Okay. Theo, Matthias, Lillian, and Cassidy are missing. Theo missed last time too. Have we had contact with Theo, meaning some of you people? Is he okay? Okay. Thank you. Okay. Well, we do have 5 of you here. There's Matthias. We have 6. I think we're close enough to get started then because we only have 30 minutes. I don't want to miss too much time. First, I wanted to start off by saying, yay, vacation, almost there. So hang in there. We're getting there. I don't know what vacation means at this point specifically because it's not like they're going to let us out of the houses and apartments, but at least that's a milestone in terms of where we're going because we've had these 3 weeks of school that we're now almost finished with. So I just want to encourage you to hang in there. We're doing this. We're learning stuff. And honestly, I think, relatively speaking, I think things are going pretty well. I think in terms of, where we are in the process. Hi, Cassidy. So just Lillian and Theo missing at this point. I posted for you guys. Hi, Theo. There he is. Okay. So I posted for you guys a lab activity, and I think it's cool. I don't know if you've played around with the FET simulation, but it's really pretty nifty, I think. And I think you're going to enjoy it. It's not quite the same thing as actually building circuits by hand, but you have a lot of options for doing things that maybe in the lab with physical equipment would be difficult because you'd be like, oh, we got to get some more wires, we got to get another voltmeter, another ammeter, set it up. It's kind of tricky. Where here you can kind of just throw stuff on there and just put things together, connect things, measure things, and pretty easily try things out. So I've posted that for you. And I've taken the assignment and I've broken it into pieces to make it not too much at the same time. There's a small assignment, I think. Anyway, I split it up. I can't remember how I did it. Oh, cool. So take a look. I think I have 3 different deadlines. I split it up into 3 different deadlines for you guys, breaking it up. And I think the first deadline is tomorrow, but it's like really small. You just have to like basically get on there and just dig around a little bit and then just say, okay, I did this kind of thing. And the 2 bigger deadlines are after spring break. That's the other thing. I think you guys all have a feeling like probably we're not going back to school on April 20th. The official announcement is still not out about that, but that's at least a plan. Probably in my mind that we're probably not coming back on April 20th, which is kind of, I'm thinking beyond the break, what kind of things we'll do. And that's one of the assignments that I've already kind of put out there for the future. In the next couple of weeks is spring break, and you definitely should take a break from schoolwork. You might have some areas where you need to catch up on things where you maybe didn't get all the assignments done or something like that. But otherwise, you should definitely plan on doing a break. I am planning on still offering something optional just to hang out if you want to. And specifically, I'm thinking about offering live streams on astronomy, which would be completely, obviously, optional, not anything related to actually what we're doing in class, not for a grade. And but I would talk about how black holes are created and that kind of stuff. And I'll let you know about that. I think that's my plan. I would offer those probably 2 or 3 times a week, just so we kind of maintain a connection. And if you guys want to just stop by and do one of those or more than one of those, you can, but you don't have to. That's definitely not mandatory. Okay, but I will post it into my group chats with the all my classes, so you know when that's going to happen. And it wouldn't be too early, obviously. Maybe like 11 a.m. Would be the earliest that I'd think about doing this, or even in the afternoon. But I think 11 a.m. feels good. That way, it's still in the morning, and it kind of gives me the afternoon to do some other stuff. And same for you guys. Maybe a reason to get out of bed. Maybe I'm being too positive about that. Yesterday, the kangaroo took up the slot for the like stream. Okay, I don't know what that means. Live stream? Kangaroo? Okay, I'm not sure. Anyway, so let's talk about parallel circuits. The lab that I gave you guys is about series circuits, and I am serious. Okay, series circuits and okay. Series circuits and parallel circuits. Yesterday we did, well, I don't know if it's yesterday. Last time we met each other online, we did series circuits. So today we're going to do a parallel circuit. Okay, so let's go back and think about what that means. So we're going to start here with a power source. R1, here is R2, and here we come back to the bottom, and this is delta V provided here. Okay, all right, that looks like it's showing up okay. Let's just kind of tilt it a little bit like that, so it's showing up okay. Okay, cool. Here we go. So we have delta V, a battery or power source. We have 2 resistors next to each other, and we're interested in what's going on here. So we've thought about this in terms of the ski resort analogy. We're going to want to continue to do that. So if we continue to do that, I'm going to pull that a little closer so we have a better of a close-up. Good, like that. So reminder, the power source in our ski resort analogy, what is that? What is a power source? Just type it in the live chat. What is the power source? Oh, okay. Yes. The voltage difference is the height, and it's provided by the ski lift. Good. So the ski lift lifts you up a certain height difference. So both those answers are actually correct. Okay. So we have over here our ski lift. Reminder about that. Here's the ski lift. So we have a seat on here. and you're holding your skis. You hold your ski poles there. There we go. And you're going up the ski lift. The ski lift is lifting you up a certain distance from the bottom to the top. Okay, that makes sense so far. Good. So let's think about what this is. We talked about the resistor. And the resistor, the skiers are being lifted up, and they then are coming down the what? What do they come down through the resistor? Each resistor is also called, in this analogy, a what? Good. The slope or the piste. So over here, let's think about this. Now, if you're the skier in this case, okay, good, slope. If you are the skier, you're coming to the top. In the circuit, of course, the skier, just a reminder about that, the skier what are skiers in the actual circuit? Well, obviously, we don't have skiers going through our circuit. What's actually moving through our actual circuit? Just type it in the live chat. Current, good. Current. So skiers per time, we would say, are a current. Good. So that's a good thing when we think about it. Now, as our skiers come out of are lifted up to the top of our power source, they are brought over here. And at that point, when they're over here, do they go through R1 and R2, or do they have to make a choice? So do the skiers have a choice or no choice? Skiers choice or no choice? They make a choice, exactly. So the skiers have a choice of either going down R1 or going down R2. So either one piste or the other piste. And you might have seen this in Austria when you were there, that, whoa, Feldmarsh says no choice. Okay, so the skiers come here at the top, and some skiers will go over on this branch, the R1 branch, and some skiers will go on the R2 branch. Okay, so there is a choice for them available. So you might have had this also in Austria, where you would get on the ski lift and you get to the top, and there might be a blue run and a green run and a black run, red run. I'm not sure what all the colors are in Europe, but there you might have different options when you get to the top. So let's kind of show this over here. So we get over here, and this brings us to the top of this, top of this circuit. So that's kind of how we pictured that. We've got the top of this hill, and then we have a choice. We can go down one side, and there might be some trees in between, okay? Or we could go down the other side, where this would be R1, and this would be R2. Now let's take a look. Oh, I see what you're saying. We'll get to what I mean by that is, of course, charges don't have actual will. They don't actually are like, I don't think I'm very good skier, so I'm going to pick the easier slope. Like I shouldn't go on the black diamond because it's going to kill me. So in that sense, they don't have a choice. But the point is, if you were a skier, you would have a choice. And the charge goes down one resistor or the other. Okay. And we'll talk about a little bit more about how they're divided and how many charges go over here, how many charges go over here. But for now, the key thing is that they do not all go through R1 and then R2, or through R2 and then R1. Some go through R1, some go through R2. We'll get to that just a second. We'll get back to that. Okay, so far so good. The next question to answer is, once the skiers have passed through R1, once the charges have passed through R1, do they go through another resistor, or are they now already at the bottom of the ski lift? Does going through just R1 get them to the bottom of the ski lift? Yes or no? They are at the bottom, right? So in our diagram, we would then say, okay, we would say now they can be brought back up by the power source providing the potential difference. Okay, so the skiers or current are lifted to the top of the slope by the power source, giving it a potential difference delta V, and then they ski down either R1 or R2 to the bottom. Okay, good. Now, let's try to interpret, not try, there's no try as Yoda would say. So let's understand now what that means, okay? And specifically, we talked about the fact that, of course, our power source moves a certain amount of current, and we could measure that. And over here, we do measure that with a turnstile. We talked about that. And we said, okay, kind of this weird look and feel thingamajigger there, a turnstile or a door that opens and closes that has a little, use your little lift pass to get through there. This is your ammeter 1, right? And it measures how many move into your power source. I think that makes sense. So we measure the certain current here, and we'll just call that the current total, I taught. Okay, the total current is measured here. Now, last time we talked about the fact that we could also have another current meter here, and that would, of course, measure the same amount because the power source just moves the currents up. Yes, amperes is the unit for current, is correct. So the current moves along here, I total. Now let's think about what happens here. What if we had another ammeter A1 here and another ammeter A2 here? A1 and A2 ammeters measuring, oh, sorry, this should be A-tote. A-tote. So, okay, I'm kind of giving this away already. So you got A-tote measuring I-tote. And then, of course, A1 is going to measure I1. And then A2 is going to measure I2. Exactly, Inessa. Tell me about that. So my question is, you have a total current that comes to this junction right here. And let's make the junction bright red. The red junction. Okay, if you look at that, how much current comes into that junction? Tell me how much current comes to that junction. Like if for example, I total, let's do an example, were 6 amps. How many of those amps would come into that junction? So let's say 6 amps is the total current. How much of that current enters the junction? The total current, all of it, correct. So 6 amps at the red junction, so we have I in, that would be 6 amps. Now let me ask you, how much current exits the junction? How much current exits comes out of that red junction? You have 6 amps entering the junction, and then you have I1 flowing this way and I2 flowing that way. How much total current is exiting the junction? Still 6 amps, of course. It's still the same amount, okay? Still the same amount exiting this way and that way. let me give you an example. Let's say, hypothetically, let's say that we know that here is 4 amps. Let's say hypothetically, I tell you I1 is 4 amps. Could you guys tell me how big I2 would have to be? So 6 amps enters the red junction. 2 amps, 2 amps. Good job. So I out, that's I1 plus I2. And if we knew that I1 is 4 amps, we could find that I2 has to be 2 amperes. Does that make sense so far? Give me a yes if that makes sense, or a Y. Just Y would be fine. Yes. Okay, cool. Great. Now, this idea right here, IN, good, excellent. I'm glad you're all with me. This idea, IN equals I out, we're going to give that a separate name. And it is called Kirchhoff's Junction rule. And it says specifically, we're still on here, that the IN needs to be equal to the I out at any junction. Okay, and that should be straightforward. There should be no surprise there. And that's why we really just call this a rule rather than a law, because Kirchhoff was very proud of this. But I mean, let's be realistic. We could have figured that out ourselves. Okay, so IN equals I out has to be true. Okay, cool. Now, let's take a look at our specific situation here, and let's finish writing things out. We just found out 6 amperes is the overall current. Over here, we know it's 2 amperes. Fine, right? We had that as well. And let's say I tell you that the total voltage is 12 volts. Delta V is 12 volts. Okay? Can you guys tell me how big R1 is if that's the case? R1 is how big? How big is the resistance of R1? Okay, 3 ohms. Now, just a reminder about that, we've got a little Idiotendreieck over here. Reminder about that. Delta V, I, and R. So in our case, I'm asking you our case. Get it? Our case? That's hilarious. So R, right, is equal to delta V divided by I. So let's take a look. Delta V, now we divide that by I1. Okay, so let's take a look. What is the voltage difference from top to bottom across R1? Well, R1 drops you all the way to the bottom of the mountain. So all 12 volts is the voltage difference across R1. Therefore, delta V is 12 volts. And I1 was given to us as 4 amperes. So we have 3 ohms as the resistance. Good. Okay. Now, how about, first of all, does that make sense? That R1 is 3 ohms. Give me a thumbs up or a Y if that makes sense to you. Yes. Okay. Yes. 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 Okay. All right. I'm going to go. Okay. Thanks. All right. Good. Let's do one more here. How about R2? How big is the resistance of R2? How big is the resistance of R2 then? 4 minutes. 6 ohms. Good. Okay, so we have 12 volts. We have 2 amperes. Is 6 ohms. It's a little small over there, but I hope it still shows up in the corner down there. 6 ohms. That's very small, but I'm going to take a picture of this. Does this make sense so far? Okay, good. Good, 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 good. Okay, good. Now, let's come down a little bit further here. And I want to ask you specifically this question. Our overall circuit, I total, we said is 6 amps. Delta V total, well, that's 12 volts. Okay. Well, how about the total resistance for our whole circuit? How much total resistance is there if 12 volts put 6 amps through this circuit? How much total resistance do we have? How much resistance are these two resistors together giving to the current? How much resistance are they giving? Okay, correct. 12 volts divided by 6 amps is 2 ohms. So let's think about this for a second. What do we have? We have here in the left resistor, oopsie, this doesn't show up very well. Let's go red. This is 3 ohms. This is 6 ohms. Okay, so we have in parallel a 3 ohm resistor and a 6 ohm resistor. The two resistors in parallel together have only, as a group, the two of them together, these two guys together have 2 ohms of resistance together. A 3 ohm and a 6 ohm together have together less resistance. So hang on a second. Hang on. No, that's not true. No, Isaac, that's wrong. I'll get to that in just a second. That's wrong. I'll get to it in a second. The first point that I want to raise is if you have two resistors next to each other, in total, they provide less resistance. And this is why it is confusing, but it makes sense. And let me just illustrate that to you. Remember, resistance is kind of like a hallway. A resistor is a hallway that is resisting you going through there. For example, a hallway of annoying 7th graders. Yes? I gave you guys a 7th grader analogy? No, I don't remember. I think I did, though. Yes or no? Annoying 7th grader analogy. I haven't talked about that. Ooh, shoot. Okay, we'll get back to that. Okay, so let's think about this like 2 lanes. Okay, I'll do the 7th grader analogy next time. But for now, let's think about this like this. 6 ohms of resistance is kind of like a narrow lane on the Autobahn. 3 ohms of resistance is a broad lane on the Autobahn. It's easier to get through this one than it's to get through this one. But even if we have this lane right here, if we open up another lane, having both lanes available for us, in total will be easier to get through than just having one lane. Okay, so you have a nice broad lane and one skinny lane that's difficult to get through, like in a Baustelle. But opening both of those up is going to make it easier for the traffic to get through. So that makes sense that therefore the total resistance should be lower. Okay, that was a qualitative arm waving argument. And I will come back to explain that more because next time I'll do the 7th grader analogy and I hope it'll make more sense. Okay, so I'll come back to that and we'll do that after break because this is it for us so far. Until break. Is that right? We don't have class tomorrow. Okay, so we'll stop there and we'll come back and talk more about it after break. If you want to play around with a FET simulation, it is pretty fun. I'll post a picture of this in our chat, in our Google Classroom. Otherwise, I hope you have a good break and you enjoy your vacation, whatever that means. And maybe I'll see you online in the next couple of weeks. If you want to come by, hang out. All right. Talk to you guys later.